break. All right, here we go. All right. So when I look at this first part, I highlighted some things, and I don't know if you highlighted the same things that I did. So it doesn't make, you don't have to highlight everything I do, but there are some things that kind of stuck out. One was a little kid eating ice cream. Oh well. And what that comes in to do is that we have learned to, we can find this chemical in the vanilla bean, but we also have artificially can make that chemical, can't we? And there is a great program. I don't know what you guys do Wednesday night at 9 o'clock. It's called Nova. Have you ever heard of Nova? It's very scientific. Anyway, they have a mini series going, and it's about chemistry. And I watched the first two, and it's really, really good. And they had a lot of stuff like we're talking about. That was on there yesterday. I don't know if they have that on now. I don't know if you could watch it because it just broadcast yesterday. I don't know if they want you to pay the $25. So anyway, if you're interested, it was really, really good. It's a whole mini series on Beyond the Elements. That's what it's called. All right, so let's go. It says here that the branch of chemistry we're dealing with carbon compounds is called organic chemistry, and yet they still consider carbon dioxide as sort of being the inorganic world, even though it's a carbon compound. But it's kind of weird because they talk about, remember photosynthesis in the 9th grade? You take the inorganic carbon dioxide and water and turn it into organic, that's food. They still kind of see that as sort of like almost an inorganic compound, but anyway, that's the one carbon compound that kind of gets slighted a little bit. It says there's more than 13 million organic compounds, and what I thought was interesting is, and this book was written over 10 years ago. So, and it says here about 100,000 new ones. 100,000 new ones are being discovered every year. So, its chances are it's up to 14 or 15 million by now. But it says by contrast, right now we only know about maybe 300,000 at the most. 300,000, not million, inorganic compounds. So it's just kind of dwarfed by the organic world. All right, so we have hydrocarbons, and we talked about that, and I have another group that's going to talk about that. And they also talked about some isomers. Now, what happens is, in part 1 of organic chemistry, I kind of go with the names that are in this book. When you get to part 2, I'm going to get to your book. You're going to get your book out, and we're going to spend a lot more time on the real names of these isomers. So that's why I don't spend a huge amount of time on that. But let's take a look at this. And when you were building models and you made isomers, let's take a look at this. This is your structural formula. What was this called here? What was the name of that? You're going to see this in books a lot. What do they call that? It's not ball and stick. Yes, space-filling molecule. That's right. And so the molecule looks maybe a little bit more like that shape than having sticks and things like that. All right, and this is called the stick structure. Remember that? And so this book calls this one N-pentane. And N-pentane would be normal, or what they call a straight chain, and they do reference the fact that it's not really straight, it's actually kind of bent, isn't it? So it's not straight, but they call it a straight chain anyway. And it even has a definition. It says here, if every carbon atom in a hydrocarbon, except for the 2 terminal ones at the ends, if it's bonded to only 2 other atoms, who you bonded to, it says here, except for the 2, bonded to only 2 other carbon atoms. So this guy here is bonded to 2 other carbon atoms, 2 other carbon atoms. Then you are a straight chain hydrocarbon. That means you're not branched. And so what is this one? Hey, I'm not bonded to 2 other carbons. See that? I'm only bonded to 1 other carbon. So that's why they have a fancy definition. It says here, branched hydrocarbons, at least 1 of the carbon atoms is bonded to either 3 or 4 carbon molecules. It's a branched one. So your book says this is pentane. They're all pentane. But you say, well, I'm going to call you N-pentane because you're straight. I'm going to call you isopentane because you have 1 branch like that. And this guy has 2 branches, and they had to come up with a name called neopentane. Is that right? Now, in part 2 of organic chemistry in your book, we'll learn that they actually have different names. I'm not going to confuse you today with that. But for right now, that's their names. All right. Now, if you are an isomer, do you have the same melting point, boiling point? Do you or not? No. And as a matter of fact, many of the physical and chemical properties are different, even though the molecular formula is the same. All right, you already knew that, didn't you? All right, so let's move on to something maybe you didn't know. Now, this one, I haven't talked about this before. And what they had is, they had this is pentane. I made a little carbon backbone, pentane. Can everybody see that? All right. Now, the one I made here was the straight chain. Got it? Okay, now they have here's what happens in organic chemistry. If carbon is single bonded to another carbon, that bond can actually rotate. Double bonds don't. Triple bonds don't. But a single bond could rotate. So what I want to show you is a thing called a conformation. So a conformation is actually the same chemical. It's the same chemical. It might have a slightly different shape. Let's take a look. Now, it says here, which carbon bond was rotated to go from the before to the after? Oh, that's this question, sorry. So what I'm going to do is, let me show what happens. Let's rotate this right here. Let's rotate bond number 1. Okay, ready? Ooh, exciting. Anything happening? Does that look like the same? Okay, let's rotate bond around bond number 2. Oh, what do you think? Do you hear me do that? Can you match that? So if I rotate around bond number 1, nothing happens, right? How about bond number 2? See what happened? Here, rotate bond number 2. Ah, that's a conformation. Now, let's rotate around bond number 3. Oh, okay. It's still the same chemical. It's called a conformation. It means that the shape is slightly different. Now, I don't study this, but there are some people in organic chemistry, they like to say that, how often do I find this shape? How often do I find that shape? Like that. Anyway, let's try this one. Which carbon-carbon bond was rotated to go from the before to the after? So let me go ahead and do this. 1, 2, 3, 4. So they want me to make iso. They want me to make this one right here. All right, is everybody with me on that? Does that look like this? Okay, so which one of these bonds is rotated to cause that? All right, what do you think? Is it bond A? Is it bond B, C, or D? Let's try D. Let's try D. Anything happen? No. Let's try A. Anything happen? Ooh. How about this one? Rotate that one. Let's see what happens. What about that? Okay, so anyway, that's yes.
Are conformations rigid?
Are they what?
Are they kind of rigid, or do they like more?
Well, that's a great question. If I discover this conformation, can it be changed? Now, yes, it can be changed, but that's a good question. If I find it in a plant and it's this conformation, why is it that conformation, and can it be changed?
I just mean, like, is it like constantly changing?
Oh,
Is it,
all right. I've never read that.
something
That's a good question. I have never read that conformations are changing back and forth. I've never read that. There had to be some force that would do that. I've never read that. Now, in benzene, remember there was the double bonds. That's called a resonance structure. Electrons are going this way. I have read that, but I've never read about a conformation that changes from one to another. Okay, so everybody okay on conformations? Now, this right here, if you go to certain places, West Virginia has, they're pretty big in chemicals. There's a big chemical place there. If you go around the United States, you can find these. Texas has some, and they're called fractional distillation or distilling plants here. And so what happens is, where do some of these organic compounds come from? And we get it from crude oil. So let's say you get crude oil out of the ground, and what are you going to do with it? What they're going to do, first of all, is heat all of it. And crude oil has a lot of things in it. And so you heat it, and so everything in there is going to turn to a gas. So you have it just hot enough to turn everything into a gas, but you're not going to have a combustion reaction. You get that? So we're going to try to keep the oxygen out and heat it, turn to a gas. And then what we're going to do is, here's the cooling tower, and it's hotter down here, and it's cooler up here. You got that? So what happens is, if you have a high boiling point, so let's pretend, I don't even know what the numbers are. Let's pretend it's 180 degrees Fahrenheit. And all of them come out at 200, and one of these guys is going to turn into a liquid at 180. So it's 200, I'll let it cool, 180, drip, drip, drip. And what comes out? This is tar. And they would use tar for like roads and stuff like that. Okay, now you gotta look. Now you still got gases. What if you have a lower boiling point? That means the temperature from 180 now it's going down, getting cooler. And now lubricating oils, they condense here, and then here's diesel fuel. It condenses there, and then here's kerosene, and then gasoline, and at the top is methane. So methane gas. Matter of fact, companies make a lot of money with this stuff. If they want to make some money with methane, they'll trap it and have to put it under pressure and store it, and it's a lot of gas. You know, a lot of places do. Have you ever been driving anywhere across the United States and you saw a flame coming out of you saw some flame and it just kept going? So, well, they're burning there. Some of them just burned the excess methane, said, I don't want that, let's get it rid. They just let it burn. Okay, so anyway, what I think is a hard thing to remember is that the high boiling points that condense first. Yeah, if you have a really low boiling point, that means it's colder. That's up here, then that's up here. But these are still kind of high. All right. The other thing they did, it talked about gasoline a little bit, and it said here that what's gasoline made of? Well, you could burn your car on hexane. It might work, but what would be bad about hexane? I don't know if you read this or not. They have a picture of a piston. You ever know how a car works? All right. So what happens is you have this gasoline that's usually mixed with some air in the carburetor. Now you got air and gas mixed up like a vapor, and they put it into the cylinder, okay? And some cars have 6 cylinders, 8 cylinders, whatever. And then what happens is the piston compresses it. It takes that gas-air mix and compresses it, and then the spark plugs are set to go off at a certain time. You don't want them all going off at the same time. You might want piston 1 going boom, then 2, 3, boom, 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 boom. Yep. So there's a timing that goes on with an engine. You get that? So what would happen if I put just hexane in my car? And it said here that what happens to hexane, it says by the time you compressed it, it would actually heat up so much, it would explode before I wanted it. I don't want you to explode now. Boom, 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 boom. And all of a sudden the engine would have knocking. The engine, it's called knocking engine. So he said, that's not good. Hexane's not good. It explodes before I told it to explode. So then we have some other ones like isooctane. And octane is 8 carbon, right? And that one works pretty well. But the key, they said, was this. They said the fuels that tend to explode too soon are the ones that were straight chains. So they made and they just arbitrarily picked this. They said, let's make an octane rating. I hereby declare that if you are N-hexane, you're so bad at being a gasoline, you get an octane rating of 0. And who's the one that's really good? The one that's really good is isooctane, and I hereby declare that your octane rating is 100. So they just set up an arbitrary scale, 0 to 100, like that. Now, the theory is that the straight chains are the ones that have low octane rates. They're not that good for your car. So the more branches, the better. And so they have a little thing here. N-pentane. Let's see, yeah. N-pentane has a rating of about this much. Isopentane, which has a branch, has a higher octane rating. Neopentane has 2 branches. It has an even higher octane rating. So the theory, the generalization is that the more branched the hydrocarbon is, the better, the higher the octane rating. Now, every state in the United States, they determine what mix of gas goes in your gas pump. And so if I go up to Alaska, it's going to be a little bit different mix than I have here. And so they do it. And North Carolina, sometimes, and they think there's too much pollutants, they'll even put 10% methanol in there to burn it a little cleaner. So they'll put some methanol in there. All right, so anyway, the question they always ask is, which one of these has the highest octane rating? It's the one with the most branches. Do you remember reading that? If you read that, you know if that's okay. All right, so I'm done. That's the first 4 pages, and are you guys doing the unsaturated? So let me get you set up. Alan sent a video. We'll be seeing Alan here next week. Where are you? Did I put a star on it? Okay. Should be here. You see your name? I didn't think you. Oh, there you are. Oh, there. That's right. And then you need to magnify. You want to just be able to scroll it, or what do you want to do?
Yeah, scroll.
Okay. Oops, I fell. That's right, be right there. All right, what do you guys present? What page is that?
It's 367 to 370. So we're mostly going to be talking about unsaturated and saturated hydrocarbons.
Okay.
So the first thing we have is like a little memory trick for what saturated versus unsaturated hydrocarbons are. So saturated hydrocarbons contain single bonds, so it's like saturated single, and unsaturated then contain multiple bonds. So
You can think of the
Saturated
double
single, right?
S's.
Yes.
Yes.
So that's a little memory trick. But to explain that a little bit more, saturated hydrocarbon means that the carbon atom is bonded to as many atoms as possible. So it has 4 single bonds. And then unsaturated hydrocarbons contain at least one multiple bond, so either a double or a triple bond. So this means that the carbon atom is not bonded to as many atoms as possible.
So for example, here is an example if you look up on the board. This is the saturated one, so it has all single, and then the unsaturated has some double, and it means that it's not bonded to as many different atoms as possible. And then, so we're going to talk about a very important unsaturated hydrocarbon, and a very important example of one is the benzene ring, which is the we have talked about that before, and has 6 carbons and 6 hydrogens, and it's C6H6 is the molecular formula of that. And the benzene ring has 3 double bonds contained within a flax hexagonal ring. And these double bonds are not fixed between any 2 carbons. Rather, they can move freely around the ring. And we talked about that in class before, and that's shown by doing the stick structure, which Gabby will demonstrate, and then just doing the little circle. You can do that instead of doing the double bonds. That shows that the double bonds can go wherever, that they're not fixed to any 2 rings. So this is one way of doing the stick.
Sure.
And then you want to show the circle one? I'll do it. And then a way to demonstrate how they're not fixated would be 1, 2, 3, 4, 5, 6, and then you would just do a circle. And that would show that they're not fixated.
So benzene is an aromatic compound because many of the compounds that contain benzene are fragrant. So an example of this is toluene, which is a common solvent which is used as paint thinner, and it's toxic, and it gives airplane glue its like distinctive odor. So a lot of compounds that have benzene as a part of it have like a distinct smell to them.
Yes, another example of an unsaturated hydrocarbon containing a triple bond instead of a double bond is acetylene, which is C2H2 is the molecular formula, so it has two
Acetylene?
acetylene. And acetylene, burning in oxygen is hot enough to melt iron, so acetylene is used a lot in the welding process.
So besides hydrogen and carbon can bond to atoms of other elements as well, which increases the number of organic molecules that can exist. So that's like another reason why there are so many organic molecules. And these are called heteroatoms. So anything that the carbon is bonded or in an organic molecule that isn't carbon or hydrogen is called a heteroatom because it's different from those two. So heteroatoms have a really profound effect on the properties of an organic molecule. And an example of this is ethene and ethanol, which differ by just one atom, oxygen, because the molecular formula for ethane is C2H6, and the molecular formula for ethanol is C2H6O. So ethane has a boiling point of negative 88 degrees Celsius, which makes it a gas at room temperature, and it doesn't dissolve very well in water. But ethanol has a boiling point of 78 degrees Celsius, which makes it a liquid at room temperature, and it's extremely soluble in water. So that can show you just like the extreme difference that just one atom or one heteroatom can make on the organic compound.
And then also organic molecules are classified according to the functional groups that they contain, where a functional group is defined as a combination of atoms that behave as a unit. And while we won't touch on all of the functional groups, I believe other students in the class will, but those are the functional groups. And then some other interesting research that we found about benzene was that it was first discovered by the English scientist Michael Faraday in 1825 in illuminating gas. And then in 1834, the German chemist Alhart Michelich heated benzoic acid with lime and produced benzene. And then it also talks about Kekule, I believe is how you pronounce it. The German chemists Joseph Loschmidt and August Kekule von Staudenitz independently proposed a cyclic arrangement of 6 carbons with alternating single and double bonds. And we had talked about that in class about how the dream of the snake, and then we had also found some interesting research about Kekule himself. There had been some other chemists today that have been saying that Kekule might have not even dreamt that, and that it was just a rumor, and that the benzene ring, the cyclical arrangement of it, had already been described by other chemists before Kekule, which I found really interesting. And then there was other reports or rumors of a dream, that another dream that he had to describe the cyclical arrangement was about I believe it was like a marriage union, and that the wife and the husband were like dancing around, and that somehow told him about the cyclical arrangement. But then it was also, there's another part that talks about him maybe having the snake dream about the snake eating itself. But some people are wondering if that was true. So those are interesting research.
And we can't ask him, he's not alive anymore. Okay,
Yes.
We can't really ask him. And I hadn't seen the bottom. Okay, they've got alkanes, alkenes, and alkynes. Okay, good.
Yes.
One thing that might not have clicked with everybody is the word aromatic, and you said it has a fragrance, but what other word means that it has an odor? What sounds like aromatic? Aroma. So aromatics they have benzene rings in them, and lots of your aromatic compounds have smells. Really, some pleasant, some not so pleasant. All right, what do you have questions about for this group? I have a quick question. Go to page 370. I know I'm putting you on the spot. Okay, you're experts on this. Why do you think there's such a big difference between ethane and ethanol in boiling points? And then I'm going to ask you, why is there a big difference in the fact that they may or may not be soluble? Ethane seems to boil what? At really cold temperatures, minus 88.
Mm-hmm.
and it doesn't like to dissolve water at all. And yet you have one oxygen atom, and all of a sudden it jumps way up to positive 78, so it's a liquid at room temperature, and it dissolves it. What do you think? Any ideas?
I know, I think for at least for the dissolving in water, the OH group makes it more soluble because it has a polar nature to it. And the
Excellent.
ethane does not have that nature to it, so that's a reason why it's not as soluble. That one's not soluble in water, but the ethanol is.
That's great. I put you on the spot. You did a good job with that one. What about the gas versus the liquid? What do you think? Anybody have any ideas?
Does it have something to do with the oxygen hydrogen bond being
Yes.
able to take a lot higher temperatures?
No,
Or
not
it
that.
changes temperatures slowly.
No, actually, what you said the first time about why it dissolves in water is, what is it?
It's polar.
Okay, so what do you think alcohols do when they're in contact with other alcohols?
They try to.
Do what?
They attract to one
So it's
another.
gonna take more energy to turn you into a gas. Remember, water should not be a liquid at room temperature, but hydrogen bonding does that. All right, that's very good, I like that. All right, thanks, who's next? Very good. Which is what? Okay, the OH, the ethanol. And that's on this picture here. That would have hydrogen bonding. That would be,
Oh, yeah, me too. But we'll do it. We'll be okay.
I'll never get an email from you guys. You guys just gonna use the camera? You guys use the camera? What are you gonna do?
Oh, yeah. Can we?
Sure.
I just.
So if you wanna, there you go. And then down there's a little box there at the bottom, and you can make it larger.
That
There you go. That's it. You guys are good. How'd you know that?
I just watched you do it.
All right, here we go. What do you guys, wait a minute. What are you guys gonna talk about?
Okay, so we're talking about phenol and the phenolic group. Okay, so this is our.
Can you tell me about what pages you're looking at?
Oh, it's page 373 to 375.
Okay, 373 and 375. Okay, I got the phenol and acidic hydroxide. I mean, phenol. That's what you're doing. Okay.
Okay, so this is an example of a phenol or a phenolic group. And first off, the difference between a phenol and a phenolic group is that a phenolic group is when it's attached to another group or functional group. So phenols contain a phenolic group which contains a hydroxyl group attached to a benzene ring. Because of the presence of the benzene ring, the hydrogen of the hydroxyl group is readily lost in an acid-base reaction, which makes the phenolic group mildly acidic. After phenol donates the hydrogen ion, it becomes negatively charged phenoxide ion, but the negative charge of the phenoxide ion is not restricted to the oxygen atom. And then on page 374 at the top, it shows the phenol, which is acidic, and then if it's a phenoxide ion with the oxygen plus the hydrogen ion to create the phenol. And then
So I don't know if they got this because they were kind of listening to you, but I know they were listening to you, but would you say this is an acid, base, or neutral? Which one is it?
it's a little bit acidic.
And why is that one more time?
Because of the presence of the benzene ring, the hydrogen and the hydroxyl group is readily lost, which is where the so the hydrogen
That's
is
the picture.
readily lost.
That's the picture of the top of the 374. right?
Yes, it's readily lost in an acid-base reaction, which makes it mildly acidic.
So when the OH is attached to some other thing, it doesn't come off, and those are alcohols, aren't they? But when the OH is attached to this, they're saying that it attracts that oxygen so well that it doesn't attract to the hydrogen, it's able to come off.
Yeah.
Okay. That's interesting.
So it is easy for the phenoxide ion to hold the negative charge because the charge gets passed around, and in the reading it kind of describes it as passing around a hot potato, like the game Hot Potato. And then because the negative charge of the ion is so nicely accommodated, the phenolic group is more acidic than it would be otherwise. And then also just the simplest phenol is called phenol. Phenols are also found in numerous household products such as aspirin and detergent, and also throat spray. And like I said, phenol is a group of organic compounds whose aromatic ring is bonded to an alcohol group, and it can also be called carbolic acid or benzenol.
So benzenol is, okay,
And it also mentions.
you know what, I just thought about that. This thing says it's called benzenol? Where'd you find that at?
Oh, I just have, this is like some extra stuff to help understand it. It's not in the
Well, I
packet.
need to know that because I don't think I knew that. You're saying that phenol is called benzenol?
Yeah, it says, it's this family, the phenols, doesn't mind being called a different name, carbolic acid or benzenol.
Okay, okay, 'cause I think some of you on your, quiz, I had asked you to name that, you said benzenol, and I don't think I gave you credit for that. I don't think I've ever heard it called benzenol. So if you did that, I'd give you back your, if you give it to me and show it to me, how did you guys know it's called benzenol? It wasn't in the packet.
I had just guessed.
Oh, yes?
Yes.
Okay, I still give it to you.
That's really nice.
Okay, go ahead, I learned something.
Okay, so because the suffix is ending in OL, the suffix is referring to the compounds that contain alcohol or OH groups. An alcohol group is present in the structure, and you can see like the OH groups attached. Phenol contains an alcohol group and is not only able to form a very strong hydrogen bond with other molecules, but this bond contributes to phenol's affinity towards polar substances. As a polar molecule, phenol is soluble in water. Other physical properties of phenol include its physical state of a colorless liquid and its high boiling point. Those strong hydrogen bonds contribute to phenol's higher boiling point. And then at room temperature, the solid form of phenol is white in color, and it's classified as having a sweet odor. So you'll notice the presence of an alcohol group, or OH, as we discussed earlier, as well as an aromatic ring. Aromatic compounds are compounds that form a cyclic ring containing double and single bonds, and it's also referred to as a benzene ring. Also, for example, benzene utilizes two intermediates, chlorobenzene and sodium phenoxide, to make phenol. Although phenol is commonly made in the laboratory using reactions, sources of phenol are commonly found in nature as well.
Where?
Many
Where did you find it?
in nature.
Where?
Many of the proteins in our body contain phenol in their chemical structure. The hormone serotonin, which gives us a happy feeling, and epinephrine, which gives us our adrenaline pumping, both contain phenol. Even our favorite natural sweetener, vanilla bean, is derived from a compound called valine, contains a phenol group.
Okay, yeah. So also part of it is like the molecular formula is C6H5OH, and then as we mentioned, it's a aromatic compound because of like the benzene ring. And then just some fun facts is Joseph Lister is the one who discovered the antiseptic value of phenol, which was then applied to surgical instruments and incisions, and so this greatly increased surgery survival rates, so that's kind of interesting. And then, so phenol was the first purposefully used antibacterial solution and antiseptic. And then phenol also damages healthy tissue, but now a number of milder phenols have been introduced, such as the 4N-hexylresorcinol, which is common in mouthwashes. So that's why we have Listerine, named after Joseph Lister. So there's a picture. And then we have a memory trick for this, just to kind of remember how it looks and that type of thing. And so that is, so it's Mr. Feeney, as in like, so
Phenol.
Mr. Fennel, like that type of thing, Mr. Fennel, Feeney, and then says, oh hi, Benny the Snitch, because then we have the O, and that's a hydroxyl group, so like O, and then just remember that's a hydroxyl group high, and then it's a benzene, so Benny the Snitch. So that's how you remember that.
That's a complicated memory trick.
Oh, it'll work.
All right, how about questions? What is the word that they use when, you said it was used to disinfect, and, what was that A word that people should know?
Antiseptic.
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 Okay, somebody know what antiseptics are? Because you can hear some other words, somebody might use the word analgesic, antiseptic, so we gotta know the difference in these words, okay? All right, questions about these? What if I wanted to get some phenol, where would I get them? I know you didn't look that up.
Sometimes,
Huh?
well, it said like sometimes they're created in the laboratory.
Okay, so they can definitely make these, synthetically
Yeah.
make them, right? All right? Yeah, go ahead.
You said something, you said like two intermediate something? I don't remember, you said something about intermediate, I kept it.
I think that was
Do you
hard,
remember when?
without visuals on that area, on your extra things, I don't think they understood the intermediate things you're talking about, is that what you're saying?
Or I just didn't catch what you said.
And
Are
then
you talking about these intermediates here, or you're talking about something else, I thought?
Is that what an intermediate is?
An intermediate would be, well, I kind of go from here and I change into this, and I change into that, and like that, so. So you were talking about some other intermediates, weren't you, or not? Didn't you talk about,
You know, from the intermediate.
yeah, okay.
I don't think.
so who was it?
Don't worry about it.
You're okay, that's right.
Inter-
I don't think or said intermediate.
I might have misheard.
Is that just
That's
it?
right. All right, who's next?
Oh, I know what you're talking about.
Okay,
Sorry.
go ahead.
I said benzene utilizes two intermediates, chlorobenzene and sodium phenoxide, to make phenol.
So you start with benzene, and then you test something as an intermediate, but your goal is not that, it's not the intermediate, it's to make phenol.
I think this is the diagram.
That's what I was
To
hoping
show
you had
it.
a diagram, yeah, that would help.
Yeah.
So we start with benzene, and are those catalysts, is that what those are? If
It's,
they're drawn on the arrow, so it must be catalysts maybe,
yeah.
what's it say?
This is, O2 FeC.
So iron something?
Yeah.
So I think the iron compound is probably the catalyst, and you're trying to get O to attach to the benzene ring, and your intermediate, is that next one show a benzene ring with an O on it?
Yeah, this is chlorobenzene and this is sodium
Oh,
phenoxide.
chlorobenzene,
Mhm.
that's chlorine, okay,
Yeah.
then you do something else, it takes the chlorine off and adds an OH to it. So that's what organic chemistry is about, this step does this step does that, those are called intermediates, okay? Alright, that's a good question, I'm glad you brought that up. So one thing I didn't like about organic chemistry, is, I don't mind building models and thinking about things, but some things in organic will say, how would you attach 3 chlorines to benzene? And you have to memorize step number 1. That puts this chlorine in. Now you have to do this. Now you have to do this. And then you have to remember all the steps to be able to put that on, all right? I didn't care for that myself, but if you take organic, and a lot of you will, that's the part. Maybe you'll like it. I didn't. All right, good job. All right, who's next? All right, and, I think, you sent me an email, I think, didn't you?
I sent it, it's only just to show a stick structure, which you can pull it up if you want, this website.
Well, okay. I'm hope we have time if you get finished, because I have some interesting things there. Now, if you don't want this, what you do is, you just, click right there and it'll give you back the camera.
Alright.
Okay.
So we're page 375 to 376. Oh no. Got tangled again.
375, 376. And even though it looks like it's pronounced ether, I've never heard anybody say ether, pronounced ether, but phonetically it looks like it should be ether.
Ugh. Okay. That's a mess. We'll get to that soon. So ethers are organic compounds which are very structurally related to alcohols. They the ones that we're going to be focusing on is ethanol and dimethyl ether. Now they have the exact same molecular formula of C2H6O, but there is a big difference between this and this bad boy. It's all about the oxygen. Now on ethanol, the oxygen is bonded to a hydrogen and a carbon, which is what makes it soluble, which makes it polar, which makes it have a higher melting point because of all the energy compacting it together. But with dimethyl ether, that isn't the same because the oxygen is connected to two carbons instead. So it's insoluble in water because it doesn't have this bond to it, which makes it insoluble, but also has a lower boiling point, which makes it a gas at room temperature, which makes a very interesting idea of a gas that is insoluble to water, which is why a little bigger version of it called dimethyl ether, but a little bit bigger, it's used for very early anesthetic because it's a gas at room temperature, but it doesn't bond to your blood, so it goes into your blood, calming you down, and then leaving throughout. This was used in the early 1800s. It's been replaced by better anesthetics, but this is the very early versions. Room temperature ravages bloodstream because of these physical properties. So a really easy memory trick that we may or may not steal, but it's a good memory trick, is if you look at this, it's either this one or that one. So either or that one.
On either side of the oxygen, right?
On either side of the oxygen. And that's how you're going to remember is the or. And then we looked up some really cool stuff, and we got really crazy with crown structures, but Kyle's going to talk about this while I untangle this mess.
Alright, so yeah, we just found like a bunch of cool facts about it. The first thing was that at room temperature, they have like a pleasant smell to them, and they're colorless. And we also found that they're very similar to alcohols, because they're generally less dense and less soluble in water, and they're relatively.
Wait. Because I thought alcohols were soluble in water. You said they're similar to alcohols because they're not soluble?
That's what this said.
We'll just skip it for now. I can double check it in a sec.
Okay.
They're relatively unreactive, and they're often used for solvents for fats, oils, waxes, perfumes, dyes, gums, and resins. They also can be used in some insecticides. The painkiller morphine, codeine is a methyl ether morphine, so codeine has parts of ether in it. And then it's also highly flammable, and it is used as starting fluid for diesel and gas engines. Dimethyl ether is used as a spray propellant and refrigerant. And methyl T-butyl ether is a gasoline additive that helps boost the octane. And I think that was basically it, other than the crown ether, which it's like this just big I mean, we'll show it to you, but it's like this big structure, and it surrounds a metal ion. And the one we did has lithium, but you can use what was it? You can use some other ones too. And let's see. They're named by using the parent name crown preceded by a number describing the size of the ring, and then followed by another number that describes the oxygen atoms. And yeah, the metal ion fits into the cavity of the crown ether and is solvated by the oxygen atoms.
So it's like, think of it like,
You move that over a little bit.
oh, sorry.
That's basically it.
Think of it, it doesn't want to untangle, but just think of it like almost, I don't want to say magnets because it's not quite, but it's holding the lithium positive ion in the middle of all of these, because if we go back to the website, all these oxygens have extra valence electrons, which are pulling on this positively charged lithium in the middle. So it's holding it in the middle as it's crowning around, like a wall around an inner town.
What do they do with this stuff?
I think they use it. Scroll up. I think they
It
just
sounds like a
used
great
it.
discovery if we could do something.
I think they just used it to help pull apart metals or something.
Yeah, they used it to pull metals out of other
Okay, so like
compounds.
metal ions were in a solution, and you want to get them out? Ah.
You can
okay.
pull it out with this kind of claw crown.
Then you just have to be able to get this stuff out.
Yeah.
But this stuff probably doesn't dissolve in water, does it?
No, it doesn't, because it's an
So
ether.
if they can grab a hold of ions and not dissolve in water, then we get skimming off the top or something like that?
Yep.
Oh, that's interesting.
This might be a do you guys know why like it either like messes with us and really relax or calm down?
I don't know.
what it is about it, but I don't, where's the packet? Where did it talk about it? I don't think it really said. It just says because of their physical properties, because
Because-
of their low solubility in water and high volatility.
It may, because it is, somewhat kind of diluting the bloodstream, may reduce the amount of oxygen to your brain while still keeping it within a safe,
That one sentence right there, sorry, I cut you off. The one sentence says, many inorganic salts can be made soluble in non-organic, in non-polar organic solvents. So if I try to put sodium dissolved in gasoline or something like that, it wouldn't work. But they're saying if you wanted to dissolve an ion, a salt, you could put it in these crown structures and that would dissolve. And that's interesting. I have no idea why you'd want to add ions to organic things like, I don't know, gasoline, kerosene, I don't know. So did they say anything about what they might be building with this?
Maybe a little bit, but when we read through it, it was mainly just an overview, and this was towards the bottom.
Okay, yeah, I've never heard of this before. So it wasn't ether, but it was an ether that formed a ring structure, wasn't it?
Mhm.
That's,
Yeah.
that's very interesting. All right, questions?
So you said it like pulls out metal ions?
What?
I think in
I
this
think
case,
so.
they're trying to put ions, I think they can pull them out, but it looks like they're trying to put ions into a non-polar material.
It's like a claw almost. You can either grab something out or put something in.
Yeah. That's interesting. Again, I've never heard that before. All right, well, thank you very much. Have a nice break. Thank you very much. We'll start with alcohol, and then we'll go amines after that, okay? So just kind of keep it in order.
I was trying to untangle it, and the moment you get it just there, it goes. It's a mess. This is exactly.
Bye-bye. I had never heard of it. And then Thank you. I never heard of it before. Thank you.
before all the Spanish stuff started, behind me, like, out in the very back west, behind me. Walk back to the rock.
Indy said something. Yeah,
I
he said something, and she
talked
agreed
to
with him.
her.
She
She just responded to it, thinking it was one of us.
Yeah, and then when she turned around, Owen gets up